All right, guys, let's begin. So my name is Vijoy. I am in Google, part of Google Networking. Today we're going to talk about the evolution of SDN control in Google's networks. And I'm probably the only speaker here who's not an open daylight consumer. And so why am I here? So two reasons. First of all, I was part of the inception of Open Daylight back in 2013. At that point, I was still in IBM, and we were, with a whole bunch of other companies, we formed Open Daylight. So I know Neela pretty well. The second reason, which is probably more relevant to this talk, is I think there are still questions about scalability of SDN, whether it's real, where are the use cases, and we see a whole bunch of people come and talk about the usage of SDN in production, Tencent and Microsoft and others, and AT&T. Think of this along the same lines. So we've been using SDN in Google pre my time. I mean, this has been happening since 2007-8. And we are pretty mature in terms of SDN deployment, and this is just one example of where we use SDN. So it's just a demonstration of proof in the pudding in some ways. Okay, moving on. So this is what the talk will go through. There are various places in Google's network where we have used SDN. In this one, we'll concentrate on server-to-server communication. So as a packet goes from one data center, traverses the WAN, goes to another data center in a Google network, it goes through literally at least 5 SDN control systems. Many more, but at least 5. And we'll be touching upon each one of those and describing what that does for us. We'll come back to this picture at the end. We'll build up on this. First, a little bit of bragging. Again, the reason for the brag is to state that SDN is real. So over the past 15 plus years, we have built one of the biggest, baddest, fastest network infrastructures on the planet. And for us, networking at Google is pretty much SDN. They are synonymous. And what are the benefits of SDN for us? I mean, again, in this day and age, people are still figuring out what SDN means. For us, it's a whole bunch of things. It's definitely not just cheap hardware. It contributes to cheap hardware, and to say that we are cheap, or the politically correct way of saying that is cost effective, is one aspect of it. But it's also, the bigger things are the next few bullets, which is it's a programmatic decomposition of the data, the control, and the management planes. So how does that help us? First and foremost, it allows independent evolution of all of those planes. So you can bring in value, bring in features, continue to evolve each one of those independent of the other. The separation of planes definitely leads to higher uptime. So unlike a box where you have mushed all of these things together, and it works against both of those bullets where you can't have independent evolution of everything in 3 different planes. Also, bugs tend to go along with the box. So a control plane bug or a management plane bug can bring down your data plane if not done right. So if you do this decomposition, you get better uptime because bugs in one plane don't impact bugs in the other, or the stability of the other planes. Finally, the distributed software control plane that we have deployed abstracts and manages complexity. And here, this is again going back to my earlier statement, why we don't use Open Daylight. We are leveraging a whole bunch of distributed systems that Google has developed for a whole bunch of other things than networking. So not just infrastructure, but even beyond infrastructure. So a lot of Google applications run on distributed infrastructure that networking tends to use and leverage. So taking something like Open Daylight and trying to munge it in that is not that trivial. Finally, the NFV piece. And here I'm not going to talk a lot about NFV as we all know it, but even if you think about SDN as a platform and you think about routing as an application or other things as an application, then you can roll out new functions in days, other than like it used to be months or even years sometimes. And even days is because you would want to canary it, figure out whether it's stable, and then roll it out globally. If you were to ignore those steps, it's actually faster than that. And it actually leads to a scale-out model instead of a scale-up model. So these, for us, are the advantages, some of the advantages of running SDN in our network. Some of the innovations that Google has done past few years that we have talked about publicly, out of this talk is primarily going to focus on those four. And the reason for those four is, again, we are going to build on that server-to-server communication. So starting from the data center side, so Jupyter, which is our building scale data center network, then Andromeda, which is a virtualization layer on that network, and then go towards the WAN pieces. So let's start from the data center side. Why make it special? So what's special about data centers? First and foremost, going back to the cheapness or the cost effectiveness, you do want to be really, really cheap when it comes to data center hardware, because there are a ton of it. There's tons of towers, tons of fabric switches, spine layers. However you build your topology, you're connecting a large scale of servers. So you really want to be cheap in the hardware you deploy. And if you want to be cheap, you end up with shallow buffers. So that's the first hit. So you do need to deal with the complexities of shallow buffer switches. But latency also is pretty important within the data center, because at least at Google, we end up building these high-performance cluster nodes. And latency, as well as tail latency, become really, really important. Shallow buffers contribute to that, but then they bring other complexities and headaches with it. The state is distributed across various elements which may not be part of the fabric. So instead of just the state being just in, say, NICs or TORs or switches, it's actually sitting in TCP stacks, it's sitting in virtual switches, it's sitting in RPC layers. So state within the data center is actually sitting in software layers as well as hardware layers. When you go out of the data center, then you get aggregated and it's primarily sitting in relatively the network, but within the data center is definitely not true. It's really large, so you have the aggregate bandwidth of the entire internet, as we'll see, within one data center, roughly 1.3 petabits. And then because of all of this, it's impossible to humanly model, deploy, observe state, react to state. It's just impossible to do that on a human manual basis. And all of this is compounded by scale. So these are typical numbers. We've seen in typical data centers, 250,000 links plus in the fabric, crossing 10,000 plus switches. On the routing plane, 10 plus million routes per fabric, and you could see up to 30,000 burst updates per minute. Traffic for us, I mean, these are, again, publicly shared numbers, 3.5 billion searches, 400 hours of YouTube traffic uploaded every minute, sorry. And all of these traffic patterns have their own characteristic. Over the past 6 years, this is again a 6-year snapshot, we've seen our traffic in data centers more than double every year to 50x within a span of 6 years. And because of that, our data center topology had to evolve. So we've gone from 4-port CRs, which are very simple designs, to in 2012 Jupyter, which actually is detailed in this paper. Last year, SIGCOMM, we published this paper, which details the topology behind Jupyter. And this is where we have reached roughly 1.3 petabits of traffic within one fabric. In this talk, I'm not going to talk about the topology ramifications of all of this. You can go and read that paper for the topology. But this is mostly about the controller bits. So the controller looks very similar to what you probably know about. It's a centralized controller, and it's clean separation of control and data plane, the purest sense of SDN you can imagine. So the FirePath controller is a logical set of controllers that provides all the control functionality. It runs this routing protocol called FirePath, which is proprietary. And the reason to go proprietary is we've dumbed it down. So it's pretty much Dijkstra and nothing else, right? So there's no overhead of the standard set of protocols that you come across in any switch. So the clients, which are the Tor switches or the fabric switches, they run a very thin agent. Again, classic control data separation. And they talk FirePath for most of the nodes that connect to the server. There are some nodes, just two are shown here, but there are some nodes that are special, and they provide connectivity for the fabric outside. And they run fabric path on one end and BGP on the other side. So just keep in mind that these nodes are special, and we'll talk about them in future slides. So you've built your data center, you've deployed a physical fabric, you have a fabric controller or controllers acting as a logical entity, control plane entity. The entire fabric acts as one control domain. So it's one switch. It's building scale. And then there are these special nodes that actually talk BGP outside and FirePath inside. Now you need to take this and make this more agile. And that's where Andromeda comes in. So Andromeda, again, is network virtualization. I think this room should be familiar with that term. It provides on-demand access to compute, is the agility bit that comes in. It provides state-of-the-art infrastructure service connectivity. What that means is pretty much every person who's running on Google Cloud has access to Google services. So whether it's Bigtable or BigQuery, some of the services that we provide and use internally, but we provide as GCP services, that access bits and how you connect to that is also controlled by Andromeda. And more importantly, it provides unique programming models. So you're not limited to layer 3 kind of programming models. You can build your own through rich APIs. And again, this picture is probably old. I'm not going to belabor this. It provides network virtualization, the logical network piece that we are all familiar with. That's the bit that it also manages, Andromeda manages. So it provides that connectivity from host VMs in Google Cloud to Google services that we've exposed to Google Cloud customers. It also manages the distributed bits of load balancing, DOS prevention, ACLs, VPN, all other NFV services that Google Cloud provides. So there are VMM bits to that, and that is managed by the Andromeda controller as well. It also manages storage pieces and things like that, but I'm not going to go into that here. So now you've got your fabric controllers, your fabric physical infrastructure, you built your Andromeda controller on top to provide agility. You have these things scattered across the globe. How do you connect them? And that's where the WAN pieces come into picture. So there are two pieces to that. The B4, which is the WAN interconnect between the data centers scattered across the globe, and then bandwidth enforcement, or BUE for short. And that does call admission control and policy management on that WAN. So this is what the B4 WAN looked like back in 2013. It's actually gotten way busier than this in the past 3 years. We have not published it publicly, but it's way busier than what is shown here. The history, a little bit of history of the B4 WAN. We started deploying this as an opt-in network back in 2010. It was fully deployed as an SDN network in late 2011, and then TE was deployed on this network in early 2012. And as you can see, the traffic has been exponentially ramping up on this WAN ever since. This is roughly what it looks like. This is a little bit more detailed than the previous pictures we showed. So consider this gray box as one B4 node. So a whole bunch of data centers in a geographic location in one neighborhood can connect to this B4 node, and you have these WAN links that connect B4 nodes across the globe. So if you blow that node up, this is the physical node topology, which is less interesting, but again, the same notion applies. We have OpenFlow agents running on those physical node switches, and then this is your B4 control element. There are OpenFlow controller bits, there are routing bits, there are distributed system bits in that B4 node control element. And again, these nodes can talk BGP ISIS for the default case when you don't have TE deployed, or something happens to TE, something is wrong with TE. You use those links as your shortest path, or that control plane element for your backup when TE fails. But typically what will happen is we have our fourth controller here, which is your TE optimization engine that manages those B4 links and does pathing based on other flow activity that you see in those fabrics. And that's the primary way of controlling the WAN. If that fails, then we back up on ISIS. So as you can imagine, a lot of the cost comes from the switches, the fiber in the data center, but the big chunk of the cost, at least on the B4 side, is the WAN links. Those are really, really expensive. And because we are cheap or cost effective, we would want to utilize those links really well. And that's where BUE comes in. Because if you were not to utilize it well, you are wasting some real big dollars on the table. So what does BUE do? So first of all, it enables efficient usage of the Google WAN links. And not just the links, but again, even in B4, we use cheap shallow buffer switches. So we need to make sure that those are well utilized and well managed. So that's number one. Number two, sharing of that WAN bandwidth based on configured policies. If you do standard 8 COSQ policies, it's not good enough. So the centralized control actually allows for really good sharing across those WAN links, not only based on Google applications like YouTube and search and Gmail and things like that, but also based on if you have Google Cloud customers and what they've paid for. It manages your bandwidth based on what you've paid for. Visibility into the thousands and thousands of users that are using that WAN. That's a big thing for us, because based on that visibility, on that telemetry, you can do a whole bunch of other things. You can optimize things better. And finally, it provides that platform where you can run experiments and you can see what works better in terms of optimization. That is actually key, because in the absence of that platform, you're stuck with what your standard routing can do. So that is key for us. And all of the previous 3 bullets actually feed into that platform. So again, we've talked about this. It's a centralized bandwidth allocation algorithm. It runs on any complex arbitrary topology. It's not limited to any topology. It does enforcement at the host, because that's the right place to do it. If you try to do it at the switches, it's not the right place to do it, based on buffers or other issues that you might run into. There is no application awareness at the switches as well. So host is the right place to do it. And it feeds into the traffic engineering bits that we talked about on B4. So all of that usage information that this controller is gathering is feeding into pathing that happens on the B4 WAN. So roughly, this control system looks hierarchical like this. So there is a global controller, global enforcer, and it goes deeper and deeper into cluster level. You can think of that as roughly the fabric level. Then a job level, and then finally a host level enforcer. So usage information from per host, per flow is sent up this tree, and then allocations, bandwidth allocations are sent, down this tree, all the way down to the host level enforcer. And this data is also sent back into the TE controller. So you can see the BW controller is doing host level enforcement and data gathering, but it's also sending that information down to the TE controller, which in turn interacts with the B4 controller to manage the paths on the B4 network using OpenFlow on these node switches. And we've talked about Andromeda and Fabric controllers. So that is roughly how a packet from a server host would go across the WAN to the other side. Key takeaways for us through this journey have been literally, this is not it's kind of a joke, but it's literally true. Think outside the box. So when you're thinking about your network, don't think box-wise. Because if you're not thinking if you're thinking network-wide and the network being the product, your way of thinking is very different. You think about a whole bunch of other things that box-level thinking does not allow you to do. One of them is the global way of thinking through a solution. So you should optimize for an end-to-end network. So don't optimize for the fabric, don't optimize just for the network virtualization layer. As you could see from the previous picture, all of these controllers interact with each other. The virtual switches, the physical switches, TE engine, bandwidth enforcer, Andromeda, all of these things are interacting with each other. Actually, it goes beyond this picture. There's interactions with the TCP stack. We just released TCP BBR. Take a look at that. So all of these interactions take place to build an optimized end-to-end picture. And if you're thinking box-wise, you will never get there. And data analytics on streaming telemetry is key. So SNMP should be dead by now. It should be all streaming telemetry, and that data should be, the collector should be scalable, where you can actually use that information to do global end-to-end optimization. Finally, SDN requires software-defined ops. You can build all the SDN you want. If you're not deploying it, modeling things in the proper way, managing things the proper way, it's all useless. So we as a community have done a really good job on progressing SDN control and data planes. It's really time now to push the management plane. And modeling bits and OpenConfig and Yang, those are just the tip of the iceberg. We have to really think about automating the deployment and the operation of this end-to-end infrastructure. And that's where a lot of the problems lie today, because if you don't do that, all of your agility in your network virtualization is moot, because you can't be adaptive to the capacity demands that you have in your infrastructure. So that's all I had. These are some of the references that you can go and read up. If there's time, I can take questions. Yep.
So when we're talking about the bandwidth engine, does the application get any say in how much bandwidth it wants, or any traffic latency characteristics? Does it say, or the network decides on it?
No, absolutely, that the application has a say. And it actually is both ways, right? So there are things that we analyze and profile and predict. And then there's also stuff that you are sure about. So if you're an application in Google or a cloud application and you're sure about certain things, you can actually quote unquote pay for it. And
how does the application interact with the network?
So that there is a feedback loop for that. So there is a feedback loop where you can buy certain network product. And there is a software loop that feeds into the allocations that we talked about in the BW control hierarchy. That allocation bit has two inputs to it. One is predefined by the app, and the other one is profiled. Does that?
Yeah.
Okay.
Yeah, you mentioned in the end the management plan. Can you elaborate more, like you mean automate deployments for your network? What do you mean exactly by managing this?
So there are a whole bunch of things. So automate deployment is one aspect. So like the work that's happening in modeling, for example, is one aspect, but that entire pipeline is opened up for like good problems to solve. For example, when you deploy things at that scale to verify if things are okay, how do you define application characteristics so that you deploy the right things? Those are all open questions that we haven't done a good job of. Yes.
So you have this end-to-end WAN deployment for applications. Two questions. One is, how many protocols were you able to eliminate from doing this controller model? Secondly, are you encrypting the data for applications because I'm traversing Euro-WAN or SD-WAN, whatever?
So on the encryption bit, yes, traffic is encrypted within the Google network. So yes, all of that traffic that is flowing on that WAN is encrypted. On the elimination bit, that's a more difficult question to answer. As you can see, we do have some aspects of BGP and ISIS in the network, but they are used as backup only. Only if some things fail or we do have to go to a suboptimal path for some reason. Other than that, there is really no, at least in this picture, there is no standard protocol running. Yes? So yeah, so there is, I mean, of course you can't look deep into the packet to do that, but at a flow level granularity, it's, you can do aggregate profiling and see what's needed, right? So you can do it, say, let's, for example, you will know that these are YouTube streams. And at that level, you know what to do. If you want to break it down per user, no. And the characteristics are pretty much per application rather than per user. So sorry, state that again.
Is there any intelligence to allow it to deal with the bigger failure? Or is the controller always required?
So it's a combination of both. I can't say anything more than that, but it's a combination of both. There are things that you would handle locally, you would have to, and then, but a lot of it is actually pushed out to the controller. We want to get as hardware agnostic as we can. And by that, I mean even the agent that runs on the switch, we want to get as agnostic as we can.
So, if you have many data centers and then you need a centralized topology view, how are you trying to keep this state in sync for this global network view? The state propagation and keeping it in sync, and since it's spread across locations, the latency is an issue. You cannot have one cluster.
So that's why you see it as hierarchical here, and it is a difficult problem. That's all I'll say, right? I mean, it's there's no shortcut to it there, but on the other hand, it is synchronized, and it took us quite a bit of time to get there. I can't say more about the implementation per se, but yeah, the hierarchy helps. Okay, so last question and then.
So since Cisco is not using any open source SDN controller, I was wondering the main reason. Is it because of the open source is not mature, or because there is some key features are missing, cannot meet the requirements of Cisco?
So I think, so the question was, why aren't we using open source? And I think primarily if you see again the history behind this predates my time even at Google. So we've been doing this since 2007 and there was nothing there. And right now we are deployed so deeply in our network that open source doesn't buy us anything. If we were to start today, definitely we would have looked at open source.
So do you think you will adopt the open source or merge your current product and get your current product open?
So let's talk about that offline because I think we are already late. And
Okay.
thanks.